Hi, pre-calculus, and welcome to a video on rational functions. There's a lot of detail in this unit, so I figured I would make a video, have you guys watch that, so in case you missed something, you can always go back and rewatch it. All right, and this video happens to be brought to you by Lonely Planet. It's a very helpful tool when you're traveling, and it's kind of an inspiration. I think sometimes, especially in the wintertime, nothing beats if you have nothing to do on a Saturday, take the train down to the city, go sit at the Borders at Rittenhouse and just sit on the floor and flip through Lonely Planets and just read the first couple pages of each one to tell you like the best of section. This is Mexico. Obviously, Mexico's a huge country and there's so much to do there, but it's one of my favorite little pastimes. Sit there on Rittenhouse Square and dream about other cultures and travel and everything. Mexico's a pretty incredible place to visit, by the way. So diverse, so close to us. I'm going there for spring break, hiking in Copper Canyon, which is in the north of Mexico. Anyway, rational functions. So a couple things to keep in mind. I'm going to mention domain. I'm going to mention how the domain impacts some discontinuities, which are specifically called holes and vertical asymptotes. And I'm also going to reference horizontal asymptotes. Okay. So the end goal is from an equation to be able to draw a good graph of the function. All right, so without a calculator, just using the equation, how can we draw a graph of something like this? Y equals x plus 2 over x squared minus x minus 6. All right, that is a rational function. Now, the parent rational function we've already studied in the unit on transformations, right? Y equals 1 over x. That is an example of a rational function. And a lot of them do end up looking similar to the parent function. But there's so much going on with this function, most likely, that it's going to be difficult to determine from the equation the transformations that have happened. Okay, so sometimes the equation simplifies to an expression that makes it easy for us to be able to shift the graph or something like that. But generally speaking, this unit is going to be different from the last one in that we're not really talking about transformations anymore. We're looking at the gritty algebra involved in working with rational expressions and rational functions and seeing how that impacts the graph. All right? First, domain. Right? The domain of a function, of a rational function, is all based off of the denominator. All right? So in math, we can't divide by 0. Right? The domain tells us which x values we can or cannot use in an equation. So because we can't divide by 0 with any rational function, all you really got to do is find the roots of the denominator. All right? That's one way to explain this based on what we did earlier in the year with roots. Which numbers would make the denominator 0? Right? So what are some x values that would make the bottom 0? Well, you have to factor. We go with factoring again for this unit. So the denominator factors x minus 3, x plus 2. So now we know essentially the roots of the denominator. It would be positive 3 and negative 2. So if x is positive 3 or negative 2, that would make the bottom 0, which we can't have. So with domain, as I said before, I recommend you write it like this. With rational functions, the domain is going to be all real numbers except for those numbers or that number that make the denominator 0. So x cannot equal 3 or negative 2. That's how we would write it. I know some of you guys were using interval notation. I would probably recommend you use this method or this notation for this part of the unit. Otherwise, your intervals, you have to write in 3 different intervals or more, and that can get a little messy. But if you want to keep with that notation, that's fine. All right. If I do ask you for range, which we'll do later, that will be from the graph. You'll graph it first, and then you'll write the range. All right. But for domain, directly based on the equation, it's numbers that would make the denominator 0. Okay. Now, notice how the numerator is also x plus 2. So the x plus 2's do cancel out, right? But that doesn't impact the domain. The domain is all based on the original equation. All right. If x is 3 or negative 2, we'd be dividing by 0. So can't do that. All right, so those x values would not produce real numbers for y, so they are not in the domain. All right, next, the discontinuities. All right, so in particular, when I talk about discontinuities with the graph, they are going to happen at these x values. All right, so on the graph, what happens when x can't equal a certain number is you often have either an asymptote or what's called a hole. Think about the parent function. Y equals 1 over x, right? A little side note here. That graph looks like this. the domain here is all numbers but 0, right? It's only 0 itself that would make the denominator 0. So what happens where x is 0? We have an asymptote where x is 0, right? The y-axis itself. So that is one thing. That's one type of a discontinuity that we can end up with, right? The other type of discontinuity we can end up with is called a hole, and holes happen when you can simplify the function. So if this factor cancels out, like in this case the x plus 2's cancel, we're left with the simplified equation 1 over x minus 3. And I do always ask you to write the simplified function. When a factor cancels out, now we can use negative 2, right? So we still can't use positive 3, but now we can use negative 2. When that kind of thing happens, that number that you can now use at the end is going to produce a hole, all right? So in other words, if a factor cancels, then the corresponding root that went with that factor is going to be a hole, all right? So we're going to have a hole in the graph, which we write as an ordered pair, where x is negative 2. And you find the y value of the hole using the simplified function. So if you plug in negative 2, you get 1 over negative 2 minus 3, which is 1 over negative 5, which is negative 1/5. So y is negative 1/5. Okay? That's how we find the y value of the hole. Now, as I said before, a number not in the domain is going to produce either a hole or a vertical asymptote. Nowhere else will they happen. All right, so we know negative 2 produced a hole because the x plus 2 is canceled, so we can now use negative 2 at the end, but we still can't use 3. So 3 is going to be a vertical asymptote, which I'll always abbreviate VA. All right, and there we have it. So if these two numbers not in the domain, they're always going to produce either a hole or a vertical asymptote, and you should be able to, from this video, figure out how you know whether 3 is going to produce a hole or a vertical asymptote. Same thing with negative 2. Right? I kind of just went through that. Now the last thing I want to go over is horizontal asymptotes. All right, so with the parent function, y equals 1 over x, we had a horizontal asymptote at the x-axis, at the line y equals 0. All right? In fact, that always will happen. You'll always have a horizontal asymptote at y equals 0 when, as in this example, when the degree of the polynomial in the numerator is smaller than the degree of the polynomial in the denominator. This is a linear polynomial. This is quadratic. Quadratic has higher degree, right? Second degree. Linear is first degree. So where that happens, we will always have a horizontal asymptote at y equals 0. All right? So that's kind of easy, just to keep in mind. You probably want to memorize that. All right? And there are reasons algebraically why that makes sense, but it's getting into some basic calculus to explain that. So I'm going to go over that in the fourth quarter, why this makes sense, okay? But don't think twice whenever the degree is smaller in the top than on the bottom. So whenever you have a lower degree over a higher degree, that means we have a horizontal asymptote always at y equals 0. All right? So now, let's draw the graph. All right? We have most of what we need to draw the graph now. All right, sometimes I will also ask you for intercepts, x and y intercepts. All right, but just using these few characteristics, we can pretty much piece together a decent graph. 8 minutes, wow. I was going to do another example, but I might call it quits after this one. All right, so the whole, negative 2, negative 1/5, we can plot that approximately, well, let's first draw the asymptotes. Let's see. So x equals 3. If we put that there, and the horizontal asymptote is y equals 0, so I'll just use the whiteboard to make that a dashed line. All right. Now, we have a hole at negative 2, negative 1/5, so that would be somewhere around there, right, where x is negative 2. And if you list the hole here on the side in your problem, you won't have to write it again. All right, that's kind of assumed. This graph doesn't open circle. A hole is. All right. Now, this graph is kind of easy to do because look at what we simplified to, right? 1 over x minus 3. So you know how I said at the beginning of the video that we're kind of not usually going to talk about transformations in this unit? This problem is one of a few rare examples of where if this simplifies to something very nice like this, where we can see the transformation, right? The parent graph shifted 3 to the right, that can help us draw a graph, right? So I'll tell you in class how we'll draw the graph completely when that doesn't happen, when it's simplified to something that's not so friendly. I'll explain to you guys what we'll need to do, which would be to make a little bit of a table and to find a couple of extra points. All right, but here we pretty much know this graph is going to be the parent function shifted 3 to the right, although it does have a hole at -2, where x is -2. Right? But the rest of it can be pretty rough. It doesn't have to be a perfect sketch. Right? But again, if I ask you for intercepts, like the y-intercept, for instance, if you plug in 0, you would get -1/3, right? So there is a y-intercept at -1/3. If you want to be a little more precise, right, you could plot that point, which would be 0, -1/3, if you wanted to be a little more exact, okay? But for the most part, I just wanted to focus on domain, how we get domain, and how this affects directly the holes and or the vertical asymptotes, all right? So these are where you're going to have your discontinuities, and one of them is going to be, in this case, a hole, because the x plus 2 is canceled. The other one will be a vertical asymptote, okay? Because we still can't use a value of 3 at the end. And the horizontal asymptote, again, that's its own entity. That's its own part of the problem. Has nothing to do with domain because it's talking about a y value. And this is all based on the degree. The degree is smaller in the top, in the numerator. And that will always be a horizontal asymptote at y equals 0. All right, that's all I wanted to go over today. So, yeah, have a good day.